Chapter 9: Atmospheric Processes and Severe Weather. This hazard affects us all. In fact, it's kind of a bonding topic across all societal groups and international borders. If you don't know what to talk about the weather. It's even mildly interesting to little kids and teenagers. This image is of an ice storm. I don't know where the image was taken, but I bet they don't get storms like this every year. In this chapter, we will learn why several types of severe weather occur and a bit about what to do to keep ourselves safe when they do. 9.1 Energy. The sun's energy drives hydrologic cycle, ocean waves and currents, and global atmospheric circulation. Remember from the climate chapter? Heat from the sun is trapped by greenhouse gases in our atmosphere, and currently there is extra heat which is driving the hydrologic cycle faster. More evaporation, more precipitation. The energy from the sun also is critical in ocean waves and currents and atmospheric circulation. To me, as a hydrologist, oceanic and atmospheric circulation is just an extension of the hydrologic cycle. Don't tell the atmospheric ocean scientists. So what is energy anyway? Well, let me remind you. Energy is the ability to do work. So when I am feeling lazy, my ability to do work is low, and I need more energy. It's a bit different for physical systems. Energy is measured in joules, J, or exojoules, EJ, 10 to the 18th joules, to describe global energy. 10 trillions of joules is typical for a thunderstorm. Hurricanes are about 100,000 times more powerful, and the image above is of the handsome Mr. Joule himself. Over the next few slides, we will briefly go over the concepts of work, force, and power. Let's first get to work. Work is done when force is applied to an object that moves it a certain distance in the direction of the applied force. It is measured in joules, which equals newtons times meters. 1 joule in everyday life is approximately the energy required to lift a small apple 1 meter straight up. The energy released when that same apple falls 1 meter to the ground. The energy released as heat by a person at rest every 17 seconds. The kinetic energy of a 50-kilogram human moving very slowly, 0.2 meters per second. The kinetic energy of a tennis ball moving at 14 miles per hour. Force is mass times acceleration, measured in newtons. 1 newton is the force of Earth's gravity on a mass of a small apple. On Earth's surface, a mass of 1 kilogram exerts a force of approximately 9.8 newtons, down. Power is the rate at which work is done. It is measured in watts, which is joules per second, or newtons times meters per second. A laborer over the course of an 8-hour day can sustain an average output of about 75 watts. A person having a mass of 100 kilograms, 220 pounds, who climbs a 3-meter high ladder in 5 seconds, is doing work at a rate of about 600 watts. So that's just a quick review. You can always refer back to this information if you feel the need. Types of energy include potential, kinetic, and heat. Again, as a review, potential energy is stored energy. Kinetic energy is energy of motion. The top cartoon is to help you remember the difference. At first, the weight is kept high off the ground. It has the potential to do some work, but for the moment, it just hangs there. Potential energy. The next, the weight is falling down, so it is in motion. Kinetic energy. Another type of energy is heat. Heat energy is energy of random motion of atoms and molecules. There are 2 types of heat. Sensible heat, which is measured by a thermometer, and latent heat, which is heat that is either absorbed or released due to phase changes. The graph on the bottom shows a substance, let's say water, At low temperature, it is solid ice. As heat is applied, the ice warms, but does not melt. When it begins to melt, the ice no longer is warming up. Instead, the heat goes into turning the solid into a liquid. That's the flat plateau in the graph, called latent heat of fusion. Once the ice is liquid water, it continues to warm as heat is added. When it is hot enough to change from liquid water to steam, again there is a plateau as heat is added, but the temperature doesn't go up. This plateau is called the latent heat of vaporization. Then as more heat is added to the system gets hotter and hotter. We use this latent heat of vaporization to cool ourselves. When sweat evaporates, heat is used up, but the temperature stays the same. Applied to weather, this latent heat is also involved as water vapor condenses to form water droplets. Heat is released. When the resultant precipitation again evaporates, heat is absorbed, making it feel cooler. Heat transfer can occur via conduction, convection, and radiation. Conduction is transferred through atomic or molecular interactions, or heat flow. Air and wood are poor heat conductors, but metal is a great heat conductor. In the cartoon, the person is holding the metal rod, has a glove on to protect their hand because the metal gets hot. If the person was holding a wooden stick, one end of the stick could be burning, but their hand would be totally fine without the glove. That's why we use wooden spoons, not metal spoons, when cooking. It also doesn't scratch your pots and pans as much, and the flavor may be better too, but the real reason is heat conduction. Convection is heat transfer through mass movement of a fluid. For example, hot air rises and displaces cool air, which falls. This creates a convection cell. In the cartoon, the blue sweater person is holding their hands above the fire to get warm, perhaps even burnt. The last heat transfer we will discuss is radiation, which is heat transfer through electromagnetic waves, such as light and infrared waves. In the cartoon, this is the green sweater person that is warming their hands to the side of the fire. This is how the sun heats the earth. Here is another cartoon summarizing heat transfer. First, find conduction. If they wait long enough, that person will burn their hand. Ouch! Next, find convection. In fact, we've got some convection cells depicted in the pot. Hot water rising, cool water falling to the bottom, where it gets warm and rises, and at the top it cools and then falls back down. Part of the cooling occurs as some heat is turned to liquid water, is used to turn liquid water into steam. There is also some convection going on in the air over the element. And last but not least, find radiation. Labeled as infrared radiation. Remember, the sun heats the earth through electromagnetic radiation. 9.2. Earth's energy balance. When discussing the atmosphere, the energy we are most concerned with is electromagnetic radiation. Electromagnetic energy travels through a vacuum at the speed of light, 300,000 kilometers per second, and is described by wavelength. Infrared radiation is involved in global warming, whereas ultraviolet light is influenced by ozone depletion in upper atmosphere. This graph is also in the climate change slides. The electromagnetic radiation from the sun is shortwave, as the sun is very hot. The electromagnetic radiation re-radiated from the Earth is longwave, as the Earth is relatively cool. I think it is interesting that the wavelengths our eyes are most sensitive to, the visible light, is the peak radiation wavelengths from the sun. The Earth intercepts only a fraction of the sun's radiation. Obviously. There is a general equilibrium between incoming and outgoing radiation, though right now we are keeping about 1.5 watts per meter squared more. Hence, the climate is warming. Nearly all of the energy available at Earth's surface comes from the sun, with the exception of heat from the Earth's core that drives plate tectonics. Energy behavior as it hits the Earth's atmosphere includes redirection, transmission, and absorption. Redirection involves reflection back to space by clouds, water, and land, as well as scattering by the atmosphere, which disperses energy in many directions. Transmission of heat is mostly to the land surface, as most energy passes through the atmosphere on a clear day. Absorption occurs as heat alters molecule structure or causes molecules to vibrate and emit energy in the form of either heat or radiation. Some of this absorbed energy may be re-emitted into space. The cartoon shows 100% of incoming radiation from the sun in yellow and what happens to it. A lot of that heat is absorbed. 19% is absorbed by water vapor, our hugest, most dominant greenhouse gas, as discussed in the climate change chapter, as well as dust and ozone. 4% is absorbed by clouds, 46% is absorbed by the land. We also have reflection of the incoming radiation, 6% off the Earth's reflective surfaces, and 17% by those white clouds. Then about 8% of the sun's incoming radiation is backscattered by molecules in the air. Let's pause and do some adding. It's all the sun's incoming radiation accounted for. 19 plus 4 plus 46 plus 8 plus 17 plus 6 equals 100. Okay, moving on to the radiation from the Earth in red. Of the 46% of incoming radiation, 15% is re-emitted as long-wave radiation. 7% is used in sensible heat transfer, and 24% in latent heat transfer. 15 plus 7 plus 24 equals 46. I think it's interesting that most of the energy received by the sun from the Earth seems to be going to changing phases of things, mostly water, from solid to liquid to vapor. Makes me take evaporation a little more seriously. So back to the cartoon. 6% of total radiation is absorbed by the atmosphere as heat is re-emitted by the Earth. This is where the greenhouse effect occurs. Other radiation absorbed from the sun is re-emitted into space. So let's add up all the outgoing radiation. 8 plus 17 plus 6 plus 9 plus 40 plus 20 equals 100. So we are pretty much in balance. We are just keeping back a teensy tiny bit. So small it disappears in rounding errors and estimates. But it is sure making a big change in our ecosystems. So more on energy behavior. Temperature depends on amount of energy absorbed or reflected. Reflection depends on albedo, not libido. Albedo describes the reflectivity of surfaces. For example, dark woodlands reflect 5% to 15% of radiation received. Light grasslands reflect about 25%. In addition, many atmospheric gases are selective absorbers, meaning that they absorb certain wavelengths of electromagnetic radiation. Examples of selective absorbers include carbon dioxide, water, and methane, as well as many more. Absorption of the energy is not reflected. Different objects absorb different wavelengths and later re-emit the radiation as the objects cool. Hotter objects radiate energy more rapidly and at shorter wavelengths. For example, compare the sun and the Earth. On the cartoon, there is a white surface with high albedo and a dark green surface with low albedo. The high albedo surface reflects the majority of the radiation and absorbs some, while the low albedo surface reflects a little of the radiation and absorbs more. For application, think of a clean white glacier. Does it have low or high